Okay, if you look at steel, so if you look at austenite, okay, austenite has FCC structure. So now what comes to your mind now? Hey, FCC, easy to deform. So now you look at retained austenite. Hey, it is easy to deform what? Austenite, right? Because FCC. Then if you look at ferrite, ferrite is BCC. Oh, it is harder now, right? If I have to compare austenite and ferrite, easier to deform will be what? Austenite. The harder to deform is ferrite. Then you look at pearlite, right? We start looking at things like, so if you look at pearlite, pearlite is in fact a compound, right? This compound is a compound, so it's made out of ferrite plus cementite. Okay. Then the next question is, so ferrite we know is what? Is BCC, right? Cementite is what? So cementite is a ceramic. It's hard and brittle. Whenever you see a term known as ceramic, it's usually what? Hard and brittle. So cementite, right? So cementite is made out of laminar plates. Right, which is okay, laminar plates, they are hard and brittle. Right? So laminar plates, okay? I'll underline the word laminar plates. And then martensite is a highly distorted BCC with limited slip. Okay, so martensite is also difficult to deform. So now when you look at this, okay, when you look at this table now, look based on microstructure. When you have ferrite and pearlite, you know, okay, ferrite is BCC, pearlite is hard. Okay, it's difficult to deform. It's difficult to deform because no doubt we have ferrite into pearlite, but he has also what? Cementite, which is hard and brittle. Then martensite, you know, is highly distorted BCC with what? Limited slip. So you reduce the slip plane, it tends to strain harden more. Okay, then you come and look at retained austenite. Retained austenite is FCC. So I'm going to show you. I'm going to show you images. Okay, so I want to show images. Especially, I want to highlight this cementite. Okay, so if we were to go into, where am I now? Okay, if we were to go into, not this one. Okay, so if we were to go into, so if we look at AISI 1045 steel microstructure. So if we look into images, I want to show you how to identify them. I wonder, is there a good one? Maybe this one is okay. Okay, this one. Advanced modeling physics is. Oh, I do apologize. Is there a good image? I need to see the image. Over here. Can it blow up? Oh no, it can't blow up at all. You know what? This is a paper I've written, and the Chinese are using it. Cheeky sort. AISI 1045. Yeah, cheeky sort. Anyway, so if you look at, unfortunately, is there any other better image? Maybe, no, I just gone through that one. Yeah, that's why it's like a cooking show, right? Cooking show, you prepare before, but this is not prepared. That's why. How about this one? No, I think I'm going to use this one. Oh, okay. Okay. So this is a piece of steel. So I'm going to we're going to zoom in. Okay. So the white region that you see down there. Okay. The white region that we all could see. Right. The white region over there that you could see. All these are all your ferrite. Okay. All these are all your ferrite. So this piece of the white regions are ferrite. The pearlite is this dark region over here. So if you go close enough, okay, you can see, right? Can you see all these lines down here? All these dark lines are all your what? Are all your cementite plates, and the white region are your what? Are your ferrite. Okay, the white region. So this is what we call our what? This is what we call our pearlite. So you can see from there. Yes, right? Okay. So now, so that's why the cementite are what? The cementite are ferrite plus what? Cementite, and cementite are the laminar plate. So we saw a combination of both. Okay, and always remember this. Okay, always remember this. Yeah, I hope. I think this is a very normal rule that we know about materials that I want to highlight. And I think most of you might have known this. If not, it's just a recap to some of you. Whenever we say a material is hard, right, it's usually related to be what? To be brittle. Okay. So brittle means low percentage of elongation, right? And low percentage of elongation usually is linked to cannot absorb energy, a lot of energy. Okay, it's not meant to absorb energy at all. So when something is hard and brittle, we know that that material cannot be used to what? Cannot be used to absorb energy. Okay, so that is what we know. Okay, then on the other side, okay, on the other side, when we have a material that is soft and is usually equal to ductile. Okay, so when you have a material that's soft and ductile, it usually means it has high percentage of elongation. Okay, in terms of steel, okay, we are looking at steel now, can absorb a lot of energy. Okay, so if I'm going to sketch the true stress strain curve, right, for Osborne, and also if we were to sketch for AISI 1045, right?
Hey, Eugene,
Yes.
what about when the material is tough?
Usually when we say a material is tough, it's usually ductile.
Oh, okay.
You can also call this tough. Okay. So if we go, if we were to do a tensile test, right, for AISI 1045 and Osborne, this is what we see. Okay, so this is 500, 1,000, 1,500, 2,000. So Osborne is very brittle, right? It's hard and it's brittle. It will strain harden. It will come here, and once it reach here, it will what? fracture. So for this case, this is our Usbo. Okay. Then I'm just going to pick AISI 1045. So if you look at AISI 1045, this is what you see. Okay, so over here, it will what? Fracture. Okay. So now, if we look at 1200, for example, if we look at 1200, right? If we have a constant stress of 1200, okay? What you will see, right? You will see over here, this is the area that Usbo will absorb, which is not a lot. It's not going to deform, right? Only when it's deformed, then it's absorbing energy. It's not going to deform. That's why we say what? Usbo will transmit the what? Energy. But when you look at, so this is your AISI 1045, right? So if when we have AISI 1045, you look at the area under here now. Okay, look at this area now. The area is so much more bigger. With so much more area over here, means it's absorbing what? It's consuming what? Energy. This energy can be impact energy, it can be bending energy or whatsoever. Okay, so that's where I want you to be able to visualize this. Okay, in terms of hard and brittle. So it has low percentage of elongation. This is epsilon for Usbo, right? Under constant stress. This is epsilon for AISI 1045. Okay, and also Usbo will fracture much earlier. But however, for this case, Usbo will not fracture yet because the stresses is not what? The stresses are not high enough. Okay, now next week I'll continue. And for this meantime, thank you for your time. And please accept my sincere apology. What I'll do is I will ask McMaster whether is there any hardware that they could change so that, I mean, I won't freeze, okay? Or maybe next week I will start using a different software to teach, okay? Before I'm going to stop recording now. Stop recording.